nice, strong foundation, and we are going to build some intuition behind some of the concepts at play here. So, truly, this is going to be decaf style. I hope that it's a nice, loving, encouraging, even relaxing way, maybe, to review or learn or study. But if you're not interested in the math, I hope you feel free to just zone out, maybe catch a tinkle or two, or maybe even just drift off to sleep. That is perfectly okay around here. So just pick whatever blesses you, and that would be perfect. Okay, so let's get started. First, let's make sure that we're on the same page as far as notation goes. So here I've drawn out a triangle because the law of sines have to do with triangles. I've labeled the vertices A, B, and C here, and the corresponding angles are also, named angle A, angle B, angle C. So in this case, whether you want to write it like this, angle A, or the measure of angle A, or just A here, we're just going to use context to decide if we're talking about the actual measure or the angle itself. Since this isn't really geometry right now, I think that's okay conceptually, right? So this angle is going to be angle A because it corresponds to vertex A, etc. Angle B, angle C. Now the key part of the notation setup here is that the length of the side on the triangle that is across from an angle has the corresponding lowercase letter. So across from angle A is side with length little a. Across from angle B is the side with length little b. And the side across from the angle C is little c here. And so as long as you have that general idea, it's okay if you have different letters or a different setup. So this might be your A, this might be your B, and this might be your C, or you might have all different letters all together, like in your notes or your textbook or whatever, right? As long as you have the corresponding lowercase letters that are across, that's perfect. Okay, so it's kind of like when you write out the Pythagorean theorem, the letters are arbitrary, A and B are arbitrary, but C tends to correspond with the hypotenuse of your right triangle, right? So same idea, we just want a nice clean setup. Okay, and then lastly, we have this vertical height here, so this is 90 degrees or perpendicular, and the length of that height is going to be h. So if we bring this vertex straight down, that length is h, or height is h. Okay, so that's our setup for today. This is going to be the arrangement here, but again, just adjust accordingly if you have slightly different lettering or notes here. So for the law of sines, let's review. We just have this ratio or this proportion that is constant, and that's why this setup is important, because the law of sines says that little a, so the length of that side over sine of the opposite angle A is equal to little b over sine of B is equal to little c over sine of C, where sine is our sine function, right? And so this ratio is constant, just kind of a cool result. And just as a little algebraic side note, you can actually take the inverse, or not the inverse, the reciprocal of each of them. So you can put the sine A over little a instead, as long as you're consistent, and that ratio still holds, or this proportion still holds. That just comes from cross multiplying and then rearranging algebraically, dividing, right? So just use whichever one is more helpful given your information, but this is the default one, and this is the one that we are going to use today. Alright, so that should be some good solid review there. So what do we mean by the ambiguous case then for this law of sines or sine law? So ambiguous means that something is unclear, but more specifically, it's unclear because it has multiple meanings. across from that angle B is 13, right there. So I have this triangle, and I'm trying to find what the measure of that angle B is. Now there's a little spoiler here. I said that this would be an ambiguous case, so there are two possible triangles, but that first default triangle that I sketch out, that I think most people would sketch out, is this one. That's the more natural default angle. Now, the other point here, spoiler, is that there's another triangle like this that actually satisfies the same given information here. Because if you look at this triangle, which I copied over here, right here, is if I have this 30 degrees, across from that 30 degrees is still 10. So that's fine. That's my little a. And across from this angle B is this 13. So that actually still satisfies it. So this triangle, according to the notation that we had before, still satisfies the across from 30 is 10, across from B is 13, and would still be fine. It would still actually satisfy the law of sines. So in this case, we have two possible answers. So I think the default sketch is this one. It makes more sense, I think, because you have your 10 and you have your 13 and you have an angle here. So it kind of makes sense to just connect that triangle. But it turns out that you can also make this 10 over here instead, and you get this triangle, which still also satisfies the notation and later the law of sines. So in this case, it's only by sketching this out that we recognize that we have this side 10, side 13, and this angle 30 degrees that is not between them. So that would be a contender for this ambiguous case. But we have more specific conditions to actually have this ambiguous case, right? So in general, you will either have no triangles that satisfy whatever conditions you're given, exactly one perhaps, or potentially two. So what are the actual conditions? It would be this. And so you can try out the different parts of this to see if you're going to be given 0, 1, or 2. But otherwise you can just go ahead and memorize this. So here we have angle A, which is 30 degrees. That is acute. It is between 0 and 90. So no problem there. Then we want to have H. H is less than A less than B. So 10 is less than 13. That's no problem. My A is less than my B. Now what about H? H is the height of this triangle. Whether you want to think of it as this one or this one, it's the same. And so how do we do that? I think it's easier to see it here. So we are going to use SOHCAHTOA, specifically this so part of SOHCAHTOA. So sine is opposite over hypotenuse. So if I have this right triangle, which is why, it's important that the height is truly perpendicular. So the perpendicular height. So if I have this angle, 30 degrees, sine of 30 is opposite. So H over the hypotenuse, which is 13. So if I consider this right triangle with H, I can set up a ratio for SOHCAHTOA. So sine 30 degrees is H over 13. You can do the algebra here, and I picked 30 degrees because 30 is a special angle for sine, right? So sine of 30 is 1/2. So H is 13 times 1/2, which is 6.5. So H is indeed less than A, less than B. So of course, take your time with the algebra, the SOHCAHTOA. If you need it, this is just meant to be a general roadmap so that things don't feel so overwhelming, right? It's just one skill, one in front of the other. So take your time with this as needed, but this is how we would find H and then confirm that H in this case is less than A, which is less than B. So this is what you would do if you needed to show all of your work, to show that it is an ambiguous case up front before you do the actual calculations. So we're going to is 1/2. So we have 10 over 1/2 is 13 over sine b. And then 10 divided by 1/2 is the same as 10 times 2. So that's 20 equals 13 over sine b. So if I go ahead and multiply sine b over, I'm not worried about 0 here. And so I multiply sine b over and then divide by 20. So I will get sine b equals 13 over 20, which I believe is going to be a nice clean decimal. 13 over 20 is 0.65. Okay, so this is where we would branch out between B1 and B2. So first we'll just do B1. So by default, if you were to type this into your calculator, if you were to do inverse sine of 0.65, most likely, unless you mess with some of the settings here, you would get just an angle between 0 and 90 degrees. So in this case, I get approximately 40.54 degrees. Okay, so that's like your default angle, which would be right here. So that's 40.54. So the other angle, this B2 angle, it turns out is just 180 degrees minus B1, which is approximately 180 minus 40.54. So approximately 139.46. Okay, so we'll talk about why they have this relationship here, but this would be your answer. You would say here, find B. So you would say ambiguous. B is about 40.54 degrees, or B is about 139.46 degrees. So that's how you'd actually answer this question. Okay, so let's look at why these two have this relationship. So why did I say B2 is 180 minus B1? Or in other words, why do the sum of their angles equal 180? So first we're going to look at this geometrically, and then we're going to look at this trigonometrically. So geometrically, I already got that B1, that B1 equals 40.54 degrees, right? So if I were to look at this triangle, right, because we considered this pivot before. So if I move this 10 over to here, I form this triangle. And if this is 10 and this is 10, then if this angle is B1, this angle is B1. It's a result from geometry. If the two sides are the same, then this angle and this angle are congruent, right? So if this is B1, and then if you look at this picture here, B1 and B2 add to equal this line, right? And that line measures 180 degrees. So this plus this, so B1 plus B2 is equal to 180. So in other words, they are supplementary. So that's how I got 180 minus B1 is 139.46. That's going to be B2. So just visually here, that's what's going on. This is B1, so this is B1, and B1 and B2 form this line, and a line measures 180. So whatever this B1 is, this B2 is going to be 180 minus that. So that is more of a geometric reason why B1 and B2 are supplementary and why their angles add to 180. You're basically looking at a triangle with some symmetry in the fact that a line adds to 180. But I think it is better to look at this trigonometrically because it gives you more of an idea of the nature of the sine function. So we are going to look at the unit circle and see why XY plane. I'm not going to go into too much detail here. Hopefully this part is review, but I hope it gives you a visual. Even if it's not review, it's a visual for why we're doing 180 minus. So if we have our unit circle and we have a point on the unit circle, it has our regular XY coordinates, right? It's on an XY plane, so we have X comma Y. Another way to represent that XY point is to draw from the origin 0, 0 to that point to make a segment, and then you measure from the positive x-axis here up to that segment to get a corresponding theta. So you start from 0 degrees and move this way. And if you go up to here, this is 180 degrees. If you go all the way around, that's 360, and you can actually keep going over and over, or even backwards with a negative angle. But basically, each point here has corresponding angles. So you go from 0 to that and make an angle there. So you have a corresponding theta. So the point here is that if I have theta and an xy pair, the relationship between them is actually, turns out that x equals cosine of that theta and y is sine of that theta. So before, when we had, when we were looking after we did the sine law and we said sine of b is 0.65, we're basically looking at sine of theta is 0.65, meaning we want the y coordinate of this point to be 0.65. So this part is 0.65. So when we do inverse sine, we get a value in quadrant 1, meaning where the angle is between 0 and 90 degrees. And in that case, we got 40.54 degrees, right? So that's our quadrant 1 value. Now, it turns out, though, when we do the 180 minus, we're actually looking in quadrant 2, because it turns out that this point also has its x comma y. That y value also is 0.65. If I look at another point here and I just flip it across this y-axis, the x value is going to be negative, but I still have a positive 0.65. And if this is theta, then the actual angle that we're looking at starting from the positive x to my point is going to be 180 minus theta. So that's what's actually going on. That's why we have 180 minus. And really, we're only looking at quadrant 1 and 2, but more specifically between 0 and 180. And that's just because when we look at triangles, the sum of the inside angles, the interior angles, add to be 180. So we don't want any angles that are greater than 180 because it forces the other two to be negative, which doesn't make sense in this context if the sum needs to be 180. And we can't include 180 because it forces the other two to be 0. So we're just only looking at interior angles between 0 and 180. So from here to here, which turns out to be quadrant 1 and 2. So that's why we're actually doing 180 minus 40.54 degrees to get the other one, 139.46. So if you wanted the x value, you do cosine of that value, cosine of 139.46. So in this case here, you have the same kind of symmetry, but this x would be negative and this y is positive, and for this one the x is positive and the y is positive. So that's what's actually going on. Now, as promised, if you happen to be taking a standardized test or a multiple choice test where you have to move a little quicker, I would just go ahead and keep in mind that if you are doing the law of sines, you might have the ambiguous case. Keep these conditions in mind. If you can do the SOHCAHTOA part quickly, then confirm the h less than a less than b to double check your answer. But otherwise, if you're given this type of information, then keep in mind that this is a possibility. And then what you can do is just get your default first angle, your b1, and then try 180 minus that. And if that value happens to be between 90 and 180, which is quadrant 2, then you realize values, or the two situations have the same y values, which correspond to the same sine value. So yeah, I hope that this was a helpful